day, guys. I hope you're all doing so well. On today's lecture, we're gonna deal with Cyclic quadrilateral, the theorem that talks about or that proves that indeed this quadrilateral is a cyclic quad. Yeah. So what is a cyclic quadrilateral? It's a cyclic quadrilateral are quadrilaterals with all vertices lying on the circumference of a circle. All points that lies on the circumference of the circle. That's a cyclic quad. Ne? So you want to prove a particular theorem that says that opposite angles of a cyclic quadrilaterals are supplementary, or they do what? When you talk about angles that are supplementary, they're saying that okay, those angles they add up to 180 degrees. That is the meaning of supplementary. Ne? So you're gonna prove that the opposite angles are supplementary, or you can just write it in this form: opposite angles of cyclic quadrilateral. This is the shortest version of this theorem. Ne? So we are given that circle with center O. Here is a circle with center O, with ABPQ on the circumference. ABPQ, these 4 points are on the circumference, such that ABPQ is a cyclic quadrilateral. I hope you understand, guys. So we are required to prove that ABP, this angle plus AQP, this angle, these two opposite angles, they are supplementary, or they add up to 180 degrees, and QAB plus QPB, they are also supplementary. So you need to prove that the opposite angles are supplementary. This angle, the add up to 180 degrees. After you've proven that, therefore, this quadrilateral is a cyclic quad. So simple, guys. Yes, let us prove. So in the examination, they could just construct for you called radi AO and OP. But if a paper or on the examination it comes as a quadrilateral with center O without this constructions line, then you must construct OA and OP in the examination, or you can construct OQ and OB. Yes. So but I have constructed for you guys AO and OP, but at some point they will never construct for you. At some point they will not do that. You need to construct for yourself. But I'll just show you how to prove it right now, guys. But for now you are required to prove this angle Q plus angle B, they equal to 180 degrees. It's so simple, guys. Let us just start. So theorem 2, let us go back to theorem number 2, guys. That where it says that if you have an angle at center, that angle at center is going to be equal to twice the angle at circumference. So let us start with O1. O1 is this angle. O1 is equals to this O1, it correlates with this angle, is equal to 2 times angle ABP, this angle, obviously angle B. I'll just say ABP. What is the reason? Angle at center is equals to twice angle at circumference. Angle at center equal 2 times angle at circumference. Similarly, O2, this angle, it relates with this angle. O2 is going to be equal to 2 times AQP. Reason, same reason. Angle at center equal 2 times angle at circumference. I have forgotten 2 times angle at circumference. The angle at circumference. I have gotten 2 times angle at. Yes. Again, do you remember, guys? O1 plus O2. These two angles, O1 and O2, are around a point. This point, center. Angles around the center, or angles around a point. This point. So when I say O1 plus O2 equal to 360, angles around a point, they equal to 360 degrees, or they add up to 360 degrees. Resin revolution. Or I can just say angles around a point. It's not a problem. Then, guys, mathematically speaking, if we have O1 here, O1 is equals to O1. This O1 is the same thing as this, is the same as this O1, and this O2 is the same as this O2. So just replace where I see O1, I put in the value that equals to O1, or I'll just put in what's equal to O1. In this case, this answer on my right hand side, or this substitution on my right hand side, is equals to O1. Basically, O1 is equal to 2 times ABP. Even on this one, I'm gonna replace O1 with 2 times APB, 2 times ABP, plus again O2 now is equals to 2 times AQB. I'm just gonna replace it. I'm gonna just substitute. Where I see O2, I put in 2 times AQP. Where I see O1, I put in 2 times ABP. Let's just like edit here. I'm gonna also do with regards to O2. O2 is equals to 2 times AQP, 2 times AQP. And we said that O1 plus O2, they equal to 360 degrees. I would also say what I've written here is going to be the same as is the same thing as what I'm writing here. So this kind of arrangement is going to be called to 360 degrees. I hope you understand, guys. Then I want to be left with ABP plus AQP on the left hand side, not 2 times. I'm on divide both side by 2. Divide both side by 2. Divide both side by 2. Therefore, ABP plus AQP equals to 360 divided by 2 is 180 degrees. I hope you understand, guys. Therefore, I've proven this theorem. You are going to prove this B plus Q equal to 180 degrees. Here it is. Similarly, if this angle plus this angle, they equal to 180 degrees. Similarly, this angle, also this angle, are going to be equal to 180 degrees. Similarly, angle QAB plus QPB equal to 180 degrees. Angle A plus angle P, 180 degrees. Angle B plus angle Q equal to 180 degrees. Therefore, ABP plus AQP equal to 180 degrees. Reason opposite angles of cyclic quadrilateral, cyclic quad. This is the reason you can use in the examination, guys. I've finished proving this theorem. Let us go to I'm just proving the converse basically. So I'm just gonna say this is one of the 3 reasons you can use to prove indeed a particular cyclic quadrilateral is a particular quadrilateral is a cyclic quadrilateral basically. So, guys, yes. So let us go to second reason you can use to prove a particular quadrilateral is a cyclic quadrilateral. Yes. So guys, here's the other reason you can use to prove indeed a particular or this quadrilateral is a cyclic quad. So we have proven this theorem number 4, the converse of it, and it. We said that if we have a line here, in this case we have a line, we have 4 sides of a quadrilateral. So if you have a line BC that makes up 2 angles, therefore these 2 angles are going to be equal to each other. Basically, angle BHC is equal to angle BDC. Butterfly angles, they're equal basically. So the reason for this kind of arrangement is that line subtends equal angles. So if this shape, or if we have 4 points on a circumference, remember, if we have 4 points on a circumference, then this is a cyclic quadrilateral. If we have 4 points that touches the circumference, 4 points of quadrilateral that touches a circumference, therefore that kind of arrangement or that kind of quadrilateral is a cyclic quad. And in this case, the second reason to use is of that theorem number 4. That says if you have a chord that subtends these 2 angles, if you have this chord, if chord subtended by the same, angle subtended by the same chord. Here we have chord BC. Chord BC, it subtends these 2 angles. If BC makes these 2 angles, therefore these 2 angles are going to be equal to each other. Angles subtended by the same chord. That is the reason you can use to prove indeed a particular quadrilateral is a cyclic quad. Theorem number 4. Go back to theorem number 4, guys. That proves, that says we have a chord here. This chord, if it makes 2 angles, therefore those angles are going to be equal. Angles subtended by the same chord. That is the reason. For this one is a line subtends equal angles. For this one, it is a line because there is no circumference. These 4 points, they don't touch the circumference, hence you call them lines. They don't qualify to be called a chord because they don't touch the circumference. But in this case, they qualify, this line BC qualifies to be called a chord because it touches the circumference. This point and this point touches the circumference, also this one and this one. I hope you understand, guys. Then this is the second reason we have already proven it, that talks about opposite angles that are supplementary. We have proven that theorem previously. Just go back to the first minutes of this video or the first seconds of this video. Then the last reason you can use to prove that indeed a particular quadrilateral is a cyclic quad is that if you have an exterior angle of quadrilateral, that this exterior angle is going to be equal to the opposite interior angle of this quadrilateral. So now for this kind of drawing to be called, for this quadrilateral to be called a cyclic quad, these 4 points needs to touch the circumference, just like here, B, C, A, D. These 4 points, they all touch the circumference. Hence, we're going to call this quadrilateral a cyclic quad because there are 4 points on the circumference. And this angle here is going to be called this angle because of what? It is an exterior angle. And this exterior angle of quadrilateral is equal to the opposite interior angle. Even if you can have a line here, line AD that extends to maybe, let me just say F. This angle here is going to be equal to this angle here, guys. I hope you understand, because this angle, it is our exterior angle, and this exterior angle is going to be equal to the opposite interior angle of a cyclic quadrilateral. I hope I understand. Therefore, this angle is going to be equal to this angle. If we prove, if they will just ask you to prove these angles are equal, maybe at some point, maybe in the activities or in the examination, I don't know, but I'm just showing you how can you prove this theorem. So the first reason you can use to prove a quadrilateral is a cyclic quad is that if a line angles subtended by the same chord, this is the first reason, butterfly angles. Then the second one is when we have opposite angles that are supplementary or that add up to 180 degrees. Then the last reason it says that if we have an exterior angle of quadrilateral is equal to the opposite interior angles, like in this drawing, like or that this is how it looks like in the on the diagram. Yes, I hope you understand, guys. Let us go to let us do some few examples that are examinable at some point. Yes. So here's an example, guys. It says that given the circle with center O, and a cyclic quadrilateral PQRS, PQRS is a cyclic quadrilateral. SQ is drawn, and SPQ, this angle is equal to 34 degrees. Determine the value of A, B, and C. Simple, guys. So remember, we have diameter here, guys. Remember, PQ is our diameter because of what? Because if you have a diameter PQ, this means that this angle is going to be equal to 90 degrees. Angle in semicircle. Remember, I hope you still remember the previous theorem number 5, if I'm not mistaken, that talks about semicircle or angles in a semicircle. I hope you understand, guys. So you have diameter PQ. If you have a diameter, and this diameter, it makes an angle at circumference. If this diameter, it makes an angle at the circumference. Therefore, that particular angle on the circumference is equal to 90 degrees. Basically, angle A is equal to 90 degrees. Angle A is equal to 90 degrees. Reason, angle in semicircle. I'm not sure, guys, how do you write it? I just write it in full. Angle in semicircle. Due to time, I'm not able to write circle in full, but you can just write it in full if there's a need. Yes. Then how do I find my B? Obviously, guys, my B, we have a triangle PQS. So in triangle PQS, angle P plus angle Q plus angle S is equal to 180 degrees. Reason, interior of triangle. Supplementary. What is the value of angle P? 34. What is the value of angle S? It is 90. What is the value of angle Q? It is B, and no, equal to 180 degrees. Then I'm going to transpose all these angles, all these two angles to the right hand side. So 180 minus 90 is 90. Then 90, I'm gonna say 180 minus 90 is 90. Then 90 minus 34 is 56. Yes, 56 here. So you can just use the calculator, it's not a problem, guys. Then the last one, 56 here. Then the last one, it's so simple, guys. So it's very simple, this one. Then the last one, we want angle C or angle SRQ. How will you find angle SRQ? They have told you go to a cyclic quadrilateral PQRS. They've told you go to PQRS is a cyclic quadrilateral. So they've told you guys ukuthi PQRS is a cyclic quadrilateral. So PQRS is a cyclic quadrilateral. Therefore, the opposite angles, here this angle P and this angle R, they are opposite angles of a cyclic quadrilateral, and they add up to 180 degrees. If I'm not mistaken, we've just proven that opposite angles of cyclic quadrilateral are supplementary. So let us do exactly what we have just proven in the start of the video. So angle P plus angle R they equal to 180 degrees. Reason opposite angles of cyclic quad. That's supplementary. So, and what is the value of angle P? 34. Angle RC equal to 180 degrees. Therefore, angle C is going to be equal to 180 minus 34 is 146 degrees. I hope you guys understand what I'm talking about here. Then the last one, it's so simple. It says that you must prove ABDE. ABDE is a cyclic quadrilateral. Which one? This quadrilateral. You need to prove that indeed it is a cyclic quad. How will you prove it? So simple, ne? Let us let me just show you some effects. You can just pause the video and prove it for me, guys. Not a problem. Prove that ABD is a cyclic quad. Ne? Remember, guys. Remember. Just now we talked about diameter, and we have diameter because due to this center gives us a green light that says that okay, indeed DC is our diameter, and our diameter makes an angle. Which angle? This angle. It makes this angle. And if diameter DC makes an angle at a circumference only, if this point is on a circumference, therefore it qualifies to be a right angled angle. Due to what? Due to this DC, that is our diameter, that makes an angle at a circumference. Angles or angle in semicircle. That's the reason. According to the proofs that we have proven in the previous lectures. So, angle DBC equals to 90 degrees. Reason, angle in semicircle. Then, if this angle is equal to 90 degrees, according to the theorem of cyclic quadrilateral, if we have a diameter, let me just draw a sketch like this. If we have an angle here, this angle is going to be equal to this angle. So if I look at this sketch is similar to this one because I can see that this angle is outside this quadrilateral, and this angle is going to be equal to this angle by default. Because of what? Because it is our exterior angle, and according to the theorem of according to one of the reasons we use to prove that a particular quadrilateral is a cyclic quadrilateral, it says that if we have an angle that is outside or if we have an exterior angle, that particular exterior angle is going to be equal to the opposite interior angle of a cyclic quadrilateral. Yeah. Therefore, DBC is going to be equal to angle E equal to 90 degrees. So each angles they equal to each angle, this angle and this angle, they're equal to 90 degrees. Each equal 90 degrees. Therefore, if these two angles are equal, then you can just conclude by saying A, B, D, E is a cyclic quadrilateral. I can just write it in full, it's not a problem. Why do I say this? Because of what? According to the reasons, according to the theorem, exterior angle of quadrilateral equals to opposite interior angle of cyclic quad. You can just use any reason, but any correct reason for this theorem, guys, not a problem. Exterior angle of quadrilateral equals to opposite interior angle. You can just write it like that, it's not a problem. Exterior angle of quadrilateral equals to opposite interior angle. You can just end it there, it's not a problem. So guys, thank you for your participation on today's lecture. You can just send your clarity seeking questions on the comment section. Any suggestions, you can just send them on the comment section, or anything just to improve this channel, you can just send any suggestions on my comment section or on my personal account. I'll just attend to your grievances, then yeah, I will address them adequately. So thank you very much, enjoy your day, Africa.